Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video, and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So this is session 20. In this session, construction of alternator, its working principle, and the winding factor. These are the topics covered. Now, synchronous generator, here a definition is given. The most commonly used machine for generation of power for commercial and domestic purposes. That means we are using a synchronous generator in a power station, say in a hydroelectric power station, a hydro turbine alternator set is used for power generation. So in a coal-fired station or a nuclear power station, a steam turbine alternator set is used for power generation. So in our power system, most of the generators are synchronous generators only, except a few induction generators which are associated with wind power. Also, diesel engine generator alternator set is used for power generation for domestic purposes. You might have seen in houses or industries and all, there will be a generator set, or that is mostly a diesel engine generator set is used for generating the necessary electric power. So it is a widely used electric machine. So you know the need of electric power nowadays. So the role of synchronous generator is very important in our day-to-day life now. Now the working principle of a three-phase AC generator, it is covered in video number 9. Say we can I'll reproduce a part of video number 9, just the working principle of synchronous generator. Now, for example, let's take the simplest possible alternator. So there are 3 coils, A dash, B dash, C dash. So how the conductors are arranged along the periphery: A, C dash, then B, then A dash, then C and B dash. That means along the periphery, these coils are arranged at an angle of 120 degrees. That is, this is the axis of coil A dash, this is B dash, this is C dash. So between these 2 coils, there is an angular difference of 120 degrees. Likewise, between B and C, there is an angular difference of 120 degrees. Same between C and A also 120 degrees. So these coils are arranged at an angle of 120 degrees each. Now assume a magnet is the center. The magnet is rotating in clockwise direction. Now the position, at this position, the magnet is, the axis of the magnet is at an angle of 90 degrees from coil A dash. Now at this point, the induced EMF in coil A is 0. That is here. This is the voltage induced in coil A, shown in red color. This is the voltage induced in coil B. This is the voltage induced in coil C. Red, yellow, and blue colors. Now when the magnet comes to the axis of A dash, now it is horizontal. Now when the magnet is in this vertical position, the voltage induced in coil A comes to a maximum. That is this point. So when the axis of the magnet was horizontal, the voltage induced in conductor was 0. Now when it is vertical, the voltage induced in conductor comes to the maximum. That means at this point. Again, when the magnet comes to horizontal position, after another 90-degree rotation, the magnet will come in this position. At that time, the voltage induced in coil B will reduce to, coil A will reduce to 0. Now, coil A comes under the influence of south pole. That means polarity of the induced EMF reverses. It goes to the negative half cycle. So I am taking this voltage as a reference. That means voltage induced in coil A can be written as Vm sin omega t. Vm sin theta or Vm sin omega t. Now next, assume coil is in the horizontal position. At that time, voltage in coil A is the maximum. Assume the magnet is in this position. That means at an angle of 90 degree with respect to the axis of coil B. Then voltage induced in coil B is 0. That means this is the point. After 90-degree rotation, the magnet comes to, or magnet aligns with the axis of coil B dash. At that time, voltage in coil B comes to a maximum. Then the magnet, when the magnet moves away by another 90 degrees, that means another 90 degree of clockwise rotation, the voltage induced in coil B will be 0. Further, it goes to the negative cycle. So when the magnet comes here, now it is along the axis of coil B dash. When it comes along the axis of coil C dash, voltage in coil C will reach maximum. That means these three voltages are reaching their maximum not at the same instant. When the magnet is along the axis of coil A, voltage in coil A will be maximum. After 120-degree rotation, the magnet will come along the axis of coil B. At that time, voltage in coil B will reach a maximum. After another 120-degree rotation, it comes to the axis of coil C dash. At that time, voltage in coil C reaches maximum. So these voltages at an angular difference of 120 degree each. They are not reaching their maximum at the same time. or they are not crossing the 0 point at the same time. See here, here, this is the point at which voltage in coil A crosses 0. Voltage in coil B crosses 0 at this position. This is voltage in coil C reaches 0 at this position. That means this angle is 120. This is also 120. Likewise, maximum between these 2 points, the angular difference is 120. Between B and C, the angular difference between these two is also 120 degrees. That means these voltages are at an angle of 120 degree each. Phase difference of 120 degrees. That means first A, then only B, then only C. That means the magnet is rotating in clockwise direction. First, the voltage in coil A reaches maximum, then voltage in coil B, and then voltage in coil C. That means voltage in coil B is lagging behind the voltage in coil A by 120. Likewise, voltage in coil C is lagging behind the voltage in B by 120 degrees and voltage in coil A by 240 degrees. So the equation for voltage in coil B can be written as Vm sine omega t minus 120 degrees. Likewise, voltage in coil C, Vm sine omega t minus 240 degrees. So Vm sine omega t, we are taking the voltage in coil A as the reference. Then voltage in coil is expressed as Vm sine omega t minus 120 degree because this voltage Vb is lagging behind Va by 120 degrees. So voltage in coil C sine omega t minus 240 degree. So voltage in coil C is lagging behind the voltage in coil A by 240 degrees. So the RMS values of this voltage can be written as Vm by root 2. Let us take it as V angle 0. Vbn is Vm by root 2. That is V angle minus 120. Then Vc, V angle minus 240. These are the voltage induced in these coils A, B and C. So V is reference. So the phasor diagram can be written as this is VA, V angle 0. This is VB, V angle minus 120. This is VC, V angle minus 240. This angle is 240 degree. This angle is 120 degrees. Now these three are coils. Say AA dash, like you can write it as A dash. Identical coils are B dash and CC dash. If we join A dash, B dash, C dash or interconnect A dash, B dash, C dash, this is A, this is A dash, B dash and C dash. We interconnect these 3 points. This is called the neutral point. I can take out a connection from there. This is the neutral point. A, C, B and this is the neutral point. So these are the voltages VA, VB, VC. These are the RMS values of voltages between A and neutral, B and neutral, C and neutral. VA, I mark it like this. VB from neutral to B, VC from neutral to C. This is VC. VC, this is VA, VB. Now we have seen the working principle of synchronous generator. Now the generator, as any other electrical machine, it has got a stationary part as well as a rotating part. So there are two types of construction for an alternator, that is armature is the stator and field system is the rotor. That is one type, which is the most commonly used type. And the other one is armature is the rotor and field system is the stator. Say in the second type, so for example here, a pair of field poles are shown in between the armature. So armature has slots on its outer periphery, which holds a three-phase winding, similar to the winding of a slip ring induction motor. A three-phase winding is there. And when the armature rotates in the magnetic field produced by the field poles, EMF is induced in it. Now the output of the armature is connected. Say three phases are there, A, B, C. The terminals are connected to slip rings attached to the shaft of the alternator. So the RYB terminals are connected here. And using brushes, we can collect current from the slip rings. This is one type of construction which is not generally used, and also for low rating machines it is used. A few alternators are there which are mainly for machines of low rating. But most of the alternators belong to this category. Armature is the stator and field system is the rotor. So for example, in this case, constructionally the outermost part is the frame. It's a cast iron frame. Inside that there is a core. Core is made up of silicon steel lamination. You know the purpose of it. Silicon steel is meant for reducing the hysteresis loss, and the laminations are meant for reducing the eddy current loss. So in short, the core losses can be reduced by using silicon steel lamination for the construction of the core. The core has slots in its inner periphery to accommodate the armature conductors. So the advantage of a stationary armature, say one advantage is the output current can be easily drawn to the load circuit. Otherwise, the output current is to be collected by brushes from slip rings attached to the shaft of the uh, armature. So it's a difficult process, but most of the commercial generators are of the rating MVA, megavolt ampere rating. So current collection through slip rings is a very difficult process in such case. So if it is a stationary armature, connection can be directly taken out. Then armature conductors can be easily braced over a rigid frame. Firm connection can be made in the armature slots. And then it is easy to insulate a stationary armature system. Then cooling is better in this case. So a fan can be provided for cooling, or ventilating ducts are provided, because of which air will be circulated through the ventilating ducts, which can cool down the machine to some extent. Then power can be tapped without any risk from the stationary part through terminal bushings. Slip rings are not required. The armature conductors are free from centrifugal forces. That is, in case of a rotating armature, any rotating body will be experienced by a centrifugal force, a force which is outward force. So in case of a rotating armature, there will be a force outward. but in case of stationary armature, that will not be there. So for mechanical stability, a stationary armature construction is better. And also for stationary armature type, only less number of slip rings are required because the two slip rings are required for supplying DC to the field system. Field system is rotating. To supply direct current to the field system, minimum two slip rings are required. Whereas in the case of a rotating armature, three slip rings minimum are required. In case neutral is to be taken out, then four will be required. So because of these advantages, most of the alternators are of stationary armature type. So the stator, the outermost part is a frame made of cast iron. Inside that, a core made of silicon steel laminations. Say in this figure, this is the frame. This is the core. Core is made up of silicon steel laminations, and the slots are there in the periphery of the inner periphery of the core. So here conductors are inserted in the core, in the slots provided in the core. So slots are generally of three types. There are open slots, semi-closed slots, and closed slots. So here conductor is placed, kept here, here conductor, here conductor in the closed slot. So each type has got its own advantages and disadvantages. So this open slot permits easy removal and easy installation, but ripples are produced in the EMF, output EMF. And also a higher value of magnetizing current. A higher value of MMF is required for in case of open slots because of the open space. Reluctance of the magnetic path is more. This conductors are to be cut by the flux produced by the field poles. Because of the open space, the reluctance is comparatively higher, so requirement of MMF is more. Whereas this is semi-closed, this is completely closed, here the requirement is less. So in these two cases, power factor will be comparatively better. But in these two cases, installation and removal are difficult. And also in this case, completely closed case, the inductance of the winding will be higher because of the presence of the core material all around. So each type has got its own plus and minus points. So the outermost part is the frame, inside that core, inside that the field system. So direct current is to be provided to the field system through two slip rings. The other type is the rotating armature type. The armature holds a three-phase winding. The terminals of the winding are brought out and connected to the slip rings on the armature shaft. And from these slip rings, current can be collected with the help of pressures. Now, rotor construction. There are two types of rotor construction. That is, one is salient pole type or projecting pole type, or the next is the cylindrical rotor or non-salient pole type. Salient pole means projecting pole. The poles are like this. So here one example is given. This is a six-pole machine. 1, 2, 3, 4, 5, 6. 6 projecting poles are there. Whereas the other type, the cylindrical rotor type, surface is smooth. So here and here the field winding is not projecting out, it is in slot. Field conductors of field winding, it is in slots on the periphery of the rotor. This is salient pole rotor. This is cylindrical rotor type. So here conductors are inserted in the slots on the periphery of the rotor. So here a connection is given, current passes, direct current is given to the field winding. So this is an example of a two-pole machine. This is a four-pole rotor, north, south, like that. So these are used on different occasions and this has got their own features. Say silent pole type, the poles are projecting out. By seeing the rotor, we can make it out whether it is a silent pole or cylindrical rotor. Poles are projecting out, that is the first difference. Here, poles are not projecting. The surface is smooth in this case. Surface is smooth. Second, for silent pole machine, air gap is non-uniform. Say here, the armature comes like this. Here air gap is less, here air gap is more. Here it is less, here it is more. In the interpolar region, air gap is more, and the polar region, air gap is less. But here in this case, air gap is uniform all around. Next, diameter is large and axial length is small. For silent pole type, it has got large diameter and small axial length, whereas for cylindrical rotor machine, diameter is small and axial length is large. Diameter is small because the cylindrical rotor machines are meant for high-speed turbo generators. And because of that peripheral velocity, to limit the peripheral velocity, the diameter is made small because it is operating at a very high speed. So for silent pole generator, diameter is large, axial length is small, whereas for cylindrical rotor machine, diameter is small and axial length is large. So silent pole machines are used for low speed alternators. So since the field poles are protruding or projecting out, windage losses are more, it can be used only for low speed machines. And for high speed alternators, cylindrical rotor construction is used. It is required for high speed alternators, as I told you, to limit the peripheral velocity. Peripheral velocity means the velocity with which a point on its surface is moving. So if the diameter is more, for the same revolution per minute, the peripheral velocity will be more. So for high-speed alternators, to limit the peripheral velocity, low diameter rotor is used. Then prime movers are hydro turbines and IC engines. Low speed ones, where prime movers are steam turbines. High speed turbines, cylindrical rotor construction is used. So this is mechanically weaker, mechanically stronger. Mechanically stronger in the sense it is uniform surface. That means no protruding part. It is capable of withstanding the friction with the wind in a better way compared to the protruding pole type or silent pole type. So depending on the need, a particular type of construction can be used, but most of the generators, a silent pole type of construction is used and low speed ones. Number of poles will be many more. Synchronous speed will be less. The next is coil span factor or pitch factor. Coil span factor means, so I'll take an example, armature, one coil. The conductors are A dash, a magnet. Now this is a single coil. This is conductor A dash, or we can say coil side A dash. Now, if the coil sides are 180-degree apart as shown in this case, if the coil sides are 180-degree apart, then the EMF induced in conductor A and conductor A dash can be added directly. Say here the EMF induced is EC, or say ES, coil side, so I'll take it as ES. If the EMF induced in one coil side is ES, then if the coil sides are 180-degree apart, as shown in this case, the EMF induced, the total EMF induced in the coil is 2 times ES. But in case coil side A is not 180-degree apart, but slightly less, assume the coil side A dash is here. Say 20-degree less, or some, it is less by some angle. Then the EMF induced in conductor A, coil side A and coil side A dash won't be in the, there will be an angular difference between the two. Say ES, ES. So in this case, assume it is less by 20 degrees. That means the angle between this point and this point, we take it as 20 degrees. Then the EMF in these two coil sides will not be directly opposite but with an angular difference. So normally it is like this, ES, ES, it can be added, that is 2 times ES. Here because of this is, assume there is a 20-degree difference between these 2 points, then the voltages also will be displaced through the same angle, that is ES, and coil side A and coil side A dash. This will be the voltages. So the total voltage in coil A is this is the total voltage. This is the phasor sum of the voltages. If the coil sides are 180-degree apart, then the EMF will be 2 ES. But in this case, it is less than that. That is the effect of a coil span. So to get the voltage in the induced in the coil, if it is placed like this, then the voltage should be multiplied by a factor called coil span factor. See, if the coil sides are 180-degree apart, 2 ES is the EMF induced. To get the actual EMF, we should multiply this with the coil span factor. Our coil span factor is defined as phasor sum divided by arithmetic sum of coil side voltages. Arithmetic sum is ES plus ES, or 2 ES. Phasor sum or the induced EMF in this case can be obtained by multiplying 2 ES with a factor called coil span factor. So coil span factor is defined as the ratio of phasor sum to arithmetic sum of coil side voltages. So in this case, the coil sides are placed 180-degree apart. Here it is less than that. 180 minus 20, 160 degree apart. Because of that, the coil side voltages cannot be added directly. So in that case, geometrically ES, suppose the coil sides are placed 160 degree apart. So there's a 20 degree difference. So the coil side voltage should be added in this manner. This is the phasor sum. So phasor sum divided by arithmetic sum is called a coil span factor. Then there is one more factor called a distribution factor. Say there are the previous example which we have considered, we have taken only one coil in each phase. Here there are three. Say for example, A, A dash, no, let's take it as 1, 1 dash. 1, 1 dash, 2, 2 dash, 3, 3 dash. Here 1 and 1 dash are 180 degree opposite. 2, 2 dash are 180 degree. So coil span factor is 1 in this case. But what is the voltage induced? These three coils, it can be written like that. This is coil 1, 1 dash, 1, 1 dash. It is connected to 2, 2 dash, which is connected to 3, 3 dash, and connection comes out. This is A. That means three coils are connected in series, and the EMF in a phase is the sum of the EMFs induced in these three coils in this case. So this is 1, 1 dash. 1 dash is connected to 2. Then 2 dash is connected to 3. From 3 dash, connection is taken out. So all these conductors are connected in series. In this case, the coil span factor is 1. That means the EMF induced in coil side 1 and 1 dash can be algebraically added. But the problem is that EMF in these coils, here there are 18 conductors. So 360 degree divided by 18 is 20 degree. The electrical angle between two adjacent slots, conductors in two adjacent slots, is 20 degrees. So the EMF induced in three coils cannot be added algebraically. Say, let's take EMF induced in coil 1, 1 dash. This is 1, 1 dash. This is 2, 2 dash. This is 3, 3 dash. They are not in phase. There is a phase difference between the voltages induced in the three coils. So again, there is a factor called a distribution factor. So it is because of the effect of distribution, we cannot algebraically add the voltage induced in coil 1, 2 and 3. We have to find out the phasor sum. So in this case, this is the EMF induced in 1, 1 dash. This is 2, 2 dash. This is 3, 3 dash. This is the phasor sum. Algebraic sum is 3 EC. EC is the coil voltage. But phasor sum is less than that. That is the effect of distribution. So distribution factor is defined as vector sum of coil voltages divided by arithmetic sum. So here arithmetic sum is 3 times EC, whereas phasor sum we have to find out depending on the electrical angle between two coils. Next, there is a factor called the winding factor. Winding factor is the product of coil span factor and distribution factor. So coil span factor is related to the coil side voltage as a single coil, and how the voltages, because of the phase difference is not 180 degrees, or the angular difference between the conductors coil sides are not 180 degrees, it's less than that, then the total EMF will be less than the arithmetic sum. Whereas in distribution factor, we consider only coil voltages. While adding the coil voltages, because the voltages in two coils are there is an angular electrical angle between two adjacent coil sides or coils. The voltages cannot be added directly, but we have to find out the phasor sum. So product of these two factors is called the winding factor. So the next term is voltage regulation. This is also a very important term in the studies of alternator. So it is defined as the change in terminal voltage between no load and full load to the full load terminal voltage. So as an equation, you can write it as no load terminal voltage minus full load voltage divided by full load voltage. That is called the voltage regulation. Or R is equal to E naught minus V divided by V. So E naught is the induced EMF. V is the full load terminal voltage. So when the alternator is fully loaded, whatever is the voltage across its terminals, that is V. So E naught minus V divided by V is called the regulation of the alternator, or voltage regulation of the alternator. So that's all for the session today. Thank you very much for attending this session. If you liked it, please share the video among your friends, subscribe for the channel, and press bell icon for notifications.